Well, if you own a spectrum analyzer or looking at getting one, do you really need a built-in tracking generator? That's the question. So I'm hoping to address that in this video with a couple of examples. And I'll show you how to address a couple of scenarios using a spectrum analyzer that has a built-in tracking generator like this one here, 8594E, and then also address the same problem using another 8594E without a built-in tracking generator. And then that should give you, I'm hoping, a good idea of whether you will require a built-in tracking generator for the projects that you're trying to solve. With that, let's get going. Okay, so what I have in front of you is a band pass filter. This is actually a no brand name, almost a white label filter. I got this on eBay. And it's got a range of 118 megahertz up to 136 megahertz. I don't know exactly if that is true range, and we'll find that out. And then it also says, it gives me some specs here. Again, I'm not sure how true these specs are, so let's see, take a closer look here. Between the spec range, the 118 to 136 megahertz, it says it's about 2 dB loss. And then between 5 to 100 megahertz, or rather 5 to 100 megahertz, and then 156 megahertz to 1 gigahertz, there's over 55 dB rejection. So that seems like a good spec for this filter. So we're going to use this as our device under test to determine the benefits of having a built-in tracking generator in your spectrum analyzer versus not. So let me get this set up. The step one will be testing this against my 8594E that does not have a tracking generator, but I'm going to use my Rohde and Schwarz SME03 and use its sweep capability between the range of this filter here. So the filter operates or passes between 118 to 136 megahertz. So I've set up my sweep. Let me get closer here so you can take a look at it. I set up my sweep here with a start frequency of 100 megahertz, and then the stop frequency at let's see, I'm going to set this up to be 160 megahertz. I'm going to scoot this just a tad bit so you can look at it. Megahertz. So 100 to 160 is how I set up the sweep, and I'm gonna let the step increment to be about 1 kilohertz, and then we're gonna let it run. So this is going to this equipment is going to sweep this bandwidth at a level of -10 dBm. All right, so that's our plan for the source for the spectrum analyzer. So the way we're going to set this up is as follows. We're going to take the output from the Rohde and Schwarz and feed it into the filter, and we'll take the output from the filter and feed it to the spectrum analyzer without the tracking generator. So let me get this set up quick and I'll be right back. Okay, so the Rohde Schwarz's output, which is this extension coax here, that's fed into the input of the filter, and the output of the filter is then fed into my 8594E that does not have a built-in tracking generator, right? So what I'm going to do here on my spectrum analyzer, I'm going to do the same. I'm going to go into my frequency and set my start frequency. I'm going to let it match my Rohde Schwarz, so 100 megahertz, and my stop frequency to be 160 megahertz. Okay, and as you can tell over here, that's the stop, and that's rather start and the stop, and we got the visual bandwidth of about 100 kilohertz. So I'm gonna use that, and first of all, let's get this running. I'm gonna go into my sweep generator. So I'm gonna scroll down to mode, and let's select that. And then right now I'm going to set it to auto. What auto does is it repeats the sweep from start to stop and goes back again, and it's a perpetual sweep generation. You could also do a single step or whatever, or single excursion and stop, or you could do it one step at a time. But for our example, I'm going to set it to auto, and I'm going to hit select. So right now, watch this section here. It says current frequency. That's the sweep it's producing right now. And if you watch the section here, the start and the stop, that's our range for the sweep. And take a look at this display here. It says RF is currently off, meaning the unit itself is not producing any RF out. So the filter is not getting any input from the sweep generator. And if you go back and look in our spectrum analyzer, there's no activity there coming in from the filter. All right. So with all that said, I'm going to go back to my sweep generator. I'm going to select turn on the RF. So right now the RF is on, and if you go back to our spectrum analyzer, you will see the sweep taking place in real time. As you can see, it's traversing from left to right across the bandwidth of 100 megahertz to 160 megahertz. It's going rather slow. That's because our step increments is 1 kilohertz. I'm going to change that to 5, and let's go back to our setup here. I'm going to scroll back up to step, select. I'm going to punch in 5 kilohertz, and that should speed up a little. So let's go back in here to our spectrum analyzer. It should move a little faster. Now, right now, what you're watching here is the peak, and it gradually dips because the filter is going to reject beyond that 136 megahertz. And on the far left, it's going to pick up again because that was a reject side of the filter behavior. Now it's picking up as a pass through, and then it's going to dip again once it gets to the other end. All right, so that's good. But what we really want to see is the frequency response through a persistent graph, so that we can visually determine what the frequency response is for this filter, where the dB peaks and where it falls, and what those measurements are, etc. In its current behavior, it's hard to measure that because it's a moving target, right? And we won't be able to justifiably say what those measurements are easily enough. So what we're going to do, in lieu of having a tracking generator again, let's go to the spectrum analyzer. There's this option called trace, and trace will allow you to hold a frequency response. So there are three buckets here, quote unquote buckets, A, B, and C. Right now we have A bucket selected, so I'm going to hold A. I'm going to let it run. So what hold does is it does a persistent capture of your high and low frequency responses in a graph like you're seeing here right now. So I'll let that run just one more iteration so we have a clear graph of the frequency response for that filter. Now once you've achieved that, which I think right now it is, I'm gonna go to View A, and what View A does, it holds it, and we can then go back to our sweep generator and we can turn off our RF, and then we can go back and also turn off our sweep generation. We don't need that anymore because we have created this persistent frequency graph, or response graph rather, and we can use it to do our measurements. Okay, so now that we have the persistent graph with the help from our sweep generator that we can use to do all kinds of measurements, not real time, but near real time. First off, we can start to show our markers. Let me zoom in quick, and you can take a look at this clearly. I hope that should come through well. All right, so I got one of the markers here, and the marker currently set up in the center here, and it is at 130.15 megahertz. There's about negative 12.31 dBm. You might be wondering, why is that negative 12 dBm? That's a lot of loss, right? According to the specs on this filter, they told us within the range there's only a 2 dBm drop, correct? So, however, the results are showing that it is negative 12.3 some dBm. And the reason why that is the case is because, if you recall, our sweep generator put out a negative 10 amplitude. So really the offset is negative 10 in there. So there's really 2 dBm loss from this filter. All right, so let's go to use our dial on the spectrum analyzer and traverse through this peak area. Or we could also go to our measure menu option on the spectrum analyzer and select the dB points. And what that does is it plots a 3 dB, negative 3 dB drop, and gives you the range. It looks like the range is about 31.2 megahertz is where you have that in between the 3 dB loss is the 31.2 megahertz bandwidth. All right, so this is just as an example to use a sweep generator in lieu of a built-in tracking generator to measure or to visually assert the performance of a filter such as this one here. All right, now imagine having to do that with a duplexer. If you were to do a similar tuning operation on a filter or a duplexer, the exercise we went through where we used the trace to hold the trace, let it plot a couple of iterations, and then determine if you need to adjust your tuning knobs or whatever of a filter. I mean, that's a lot of back and forth. And in my humble opinion, that's a terrible waste of time. So while the sweep generation option works well as a plan B, ideally you would want a real-time tracking generator that you can use to real-time fine-tune your filter or duplexer. Now you could also use instead of using a sweep generator like we did here, you could use a noise generator and use that as a source into your filter, and then examine a similar operation through the help of a noise generator. I don't have access to a noise generator in my lab, but I am getting one, so I will probably be using that to do some experiments and such. But for now, I hope you get the idea that it's an iterative process to kind of build this frequency response plot for you to do some measurements and whatnot. Now, one of the other measurements I would like to kind of draw your attention to is if you go down further or zoom in a little, and you can take a look at it over here. I'm going to move the marker and let's see what is the when really does the reject kick in. It looks like it starts to kick in at about here 138, which is per spec. I mean, it says between 118 and 136 is a bandpass filter. I believe at 137 or something it kind of drops and continues to drop, right? I mean, if you look at the dBm here, you will see it continues to drop, and then I believe that's the lowest point. There's about negative 72 dBm, so which kind of falls within the spec of greater than 55 dB drop here. So anyway, so that's a quick view of using a sweep generator to build a frequency response plot to do measurements on your filters. Now, if you want to do a filter tuning as in a duplexer, you would follow a similar workflow, but then you will, if you need to tweak the waveform to a particular response, then the process becomes iterative and you would have to go through the cycle. I mean, we only did this one cycle, right, for us to build this plot. But if you were to do a tuning and tweaking of your filter as in a duplexer, then the process becomes tedious and iterative and time consuming. So I hope you get to appreciate the downside of not having a tracking generator, at least partly. Once you start seeing the other side of this video, which is using a tracking generator, you'll see how much of a time difference there will be and time benefit. So let's switch over to my other spectrum analyzer. where we can start using its built-in tracking generator to measure the frequency response of this filter. Let me get that set up and I'll be right back. Okay, so I'm here in my other spectrum analyzer with the built-in tracking generator, and I hooked up the tracking generator's output into the input of the filter, and then the filter's output goes to the tracking generator's RF input in the back end there. All right, so I'm going to put this aside, and let's try to zoom in. And what I'm going to do first is I'm going to set the tracking generator, or rather, let's first set the frequency. We're going to do the same thing, start frequency at 100 megahertz, and the stop frequency was 160 megahertz. So we have the same setup here. We have the start at 100 megahertz and stop at 160 megahertz, and the visual bandwidth is 100 kilohertz. And right now I'm going to go into my tracking generator's menu option. Let me get that set up and I'll be right back. Okay, so for us to activate the tracking generator, there is this option here called the auxiliary control. Let's select that, and then that takes you to the tracking generator menu. Let me zoom in a little, and so you can see it well. Right now I'm going to select my track gen, and right now if you look at the top menu option, it says off. I'm going to turn it on. When I turn it on, I want you to keep an eye on the screen here. See how fast the equipment plots the graph. And you can then quickly appreciate the amount of time one would save by having this tracking generator do a real-time plot. Because what a tracking generator does is it tunes itself to that same start and stop frequency. So you're not having to reset it up or stage it or any of that stuff. So it's a fairly real time, it's in lockstep with what you are monitoring from a frequency standpoint, and works in the same clock cycle. So which is great, right? So let me turn this on. That is so fast. And this is real time. Right, so we're not having to do with the trace or holding the trace or building out a persistent graph for us to build this real-time frequency response. So as you can tell, this is real time. So when I turn the tracking generator off, it's gone. Let's turn it back on again. There you go. Now I'm going to go to my marker like we did in our previous example. Go back to marker. Again, we have the same frequency response here. We have a 130 megahertz at negative 12.13 dBm. So you might be asking, why is there a negative 12 on this example when we are not using the Rohde and Schwarz sweep generator? Well, the answer to that is the built-in tracking generator puts out a negative 10 dBm also. So by default, that's the amplitude that the built-in tracking generator operates in. So there's an offset of 10 dBm in this behavior. All right, so with that said, let's go back to our measure. We're going to do the same thing, right? Only all of this stuff is real time. So now we are looking at the two arrows here that mark the negative 3 dBm points, and it's about the same like we watched in our previous example. 30.15 megahertz is this bandwidth here between the 3 dB drop. And let's go use our marker, and I'm going to move the marker to the bottom section here like we did with our previous example. I believe that's the lowest point, and you're looking at negative 72.3747 dBm, which again fits the spec of this bandpass filter. So one of the examples that we haven't covered here is the real-time tuning of filters and duplexers, which I will do in the next video. But really I wanted to quickly show you and allow us to appreciate the benefit of time and the amount of effort that's otherwise required without a tracking generator between the two examples we just saw. Well, I hope this was helpful, and I truly have learned quite a bit between experimenting between the two spectrum analyzers, one with and one without a built-in tracking generator. So I can sincerely appreciate the value of having one built-in. Well, with that, thanks for watching. I know this has been a kind of a long drawn video here, so I hope this was useful. Thanks for watching. We'll talk soon, and God bless.